Welcome everyone. In this video I'm going to show you my new toy, which I managed to get from eBay for a very cheap price. This is a Solartron 7060 digital multimeter. It's a huge benchtop multimeter, but it's relatively precise and it has very nice options. So I wanted to buy this thing. And I managed to get this thing from eBay for 170 euros, so it was relatively affordable, I would say. And it has just a few aesthetic defects, which I will show you later. And also it has some electrical issues, which I will try to, let's say, repair in this video. But otherwise it still works well, and it provides the proper number of PPMs as well. So hopefully this video will be useful to you if you are interested in these kind of old multimeters. And this multimeter has a relatively high resolution. It's a 6.5 digit multimeter or voltmeter. And if I try to translate some of these data into more understandable data, then I can say that, for example, if we are measuring DC voltage with this thing, we can measure up to 1 kilowatt, and the resolution of this thing is 1 microwatt. Similarly, if we check the DC current, then the current resolution is 1 nanoamp, and we can go up to 2 amps as the maximum measurable current. It can also measure resistance, and it can measure resistance with 4-wire measurement or Kelvin measurement, and the lowest value is 1 milliohms, and it can go up to 200 mega ohms, and it has an RMS AC measurement possibility as well, from 1 microwatt up to 750 volts. So this is all nice. I can show you also the panel of this. So here we have the main switch, and I just turn this on just to preheat the specimen a little bit. You will see here some animation, and then a welcome message and the GPIB address. And now you can see those numbers fluctuating as the sockets here or in the back of the panel, which I will show you later, the sockets are floating. So I will just take some plugs and short the input wires or the input terminals, just to remove any kind of jumping numbers. So now I shorted the inputs, and you can see that there is still a small residue voltage, and that will stay there for a while. But what I can show you is that we can measure voltage in DC and AC. We can measure resistance with the 4-wire arrangement, and then we can measure DC and AC current, and we can null the display. And this null is especially useful when we use the 4-wire arrangement for measuring the resistance of a resistor or something, because we can short the leads, and we can get rid of the resistance of the leads. So we specifically measure only the component. I can press this now, and then you see the message. And we also got rid of the, let's say, offset, which was visible with the shorted inputs. On this side, we have auto range. That's the most convenient thing to use, and then all these other things are related to the manual range selection. And then we have a sample and track option, as well as a filter option. That's of course for longer integration times but more stable readings. We have a ratio here. We have 6 times 9. This is when we can put the multimeter into the 6.5 digit mode, kind of, because by default it's only 5 times 9 displays shown there. And then we can switch the beeping on and off, and sometimes we can trigger the remote mode here. And there is a hidden button here. If I press this, then it will show the GPIB address. There was it. And then here we can connect the guard internally to the low LO socket here. That is for some sophisticated measurements, especially when we want to measure very high resistances. So then this helps us to avoid noise. And then this is for the 4-wire measurement, the other button. And before showing you the back of this thing, I will connect my, let's say, voltage reference to the input, so we will see how this measures the voltages. So I connected my reference to the multimeter. So here, this is just a 12-volt input. Then there is a DC-DC converter here, which brings the 12-volt up to 15 volts. And that will be the input voltage of the voltage reference. And that voltage reference, I just bought it from Banggood. It's a very simple voltage reference. And it can output 4 different voltages, 2.5, 5, 7.5, and 10 volts. And each of these values were measured by the people who assembled the circuit, which is inside this box, and they wrote down their parameters. So at least I can compare those values with these values, but I don't know which one I can believe more. But keep in mind that this device is like 32 years old, a rather old device. So it might be that the calibration of this really moved away. And then maybe the thing which was used to measure the voltages on this device had a better calibration. So we will see. And the first thing that you can see is that there is only 5 digits on the display right now. And I'm connected now to the 2.5 volts, and we are measuring 2.5011. And as I said, there's a button here which says 6 times 9. If I press this, it will put another digit here. So those who like PPMs can have one more digit there. And of course, this will drift a little bit as everything gets to the room temperature or to a somewhat higher temperature, because I just turned on these things. And for example, this guy here says that it needs at least 1 hour of running time to get all the internal circuits at a stable, let's say, state. And I guess the voltage reference also needs some on time, but this is just recently turned on, so those numbers can creep a little bit. But we can see that the 2.5 volt is now 2.50111. And then we can see the 5 volts. And now I'm connected to the 5 volt, as you can see, and that is 5.00882 or 3. It's fine. That is a very low fluctuation, and I will compare this as well to the data sheet value of this voltage reference. And then let's see what we can measure at 10 volts as well. So now we are at 10 volts, as you can see, and we have 9.99610. A little bit below 10 volts, but it's not too bad, because as you can see, let's say this digit is millivolts, so 4 millivolts or less than 4 millivolts, 3.9 millivolts away from 10 volts. That's pretty okay. So basically this is all about the device in a nutshell. You can see that it works. Now I'm going to show you the side of this thing, and I will also show you the back panel, because there is also some interesting stuff there. So this is the side panel, and as you can see that something is missing from here. So actually this thing has some kind of handle like a luggage. So there is a belt kind of thingy here, and there is also a plastic cover here, but that is obviously missing, and is the same on the other side. So I will try to come up with something. Either I will put a metal strip here, for example, a piece of aluminum, or I will 3D print something from several pieces, probably 3 because of the size of my 3D printer's heated bed. And then there are a few slots for bolts. So I can actually cover this up and make this a little bit nicer. So as you can see, it's not the most aesthetic stuff, but I don't care. I care about the inside of this thing and not the actual look. And now probably a little bit more exciting part. This is the back panel of this thing, and we should start from the right side. So this has a very interesting input panel and input selector. So this is just a regular 3-pin C13 connector, if I'm not wrong. And then here there is a socket for a fuse. And then there are 2 switches, which is very interesting. So there are 2 voltage levels. One is 120 and the other is 240. And next to that selector, there is a low and high selector. And what they do is very funny because, for example, if with the voltage selector you select 120 volts, then if you select low, then the input voltage should be 100 volts. But if you select high, then the input voltage should be 120 volts. And it works in a similar way with the 240 volts. And how this works is that if you select 240 and low, then that should result in a 220 input voltage. And then if you select high, then that should be the 240. And of course, the different voltages will require the different fuses as well. And then on this side, we have the GPIB interface, or HPIB, or IEEE 488. So yeah, the same standard has different names. So this is a 24-pin socket here. And here we have dip switches. And this dip switch panel is used to select the address and to control the behavior of this device. So that's what we have here. This GPIB connector might be discussed in a future video if I manage to finish my software for communicating with this thing. And then here there is a sticker saying 1990. So as I said earlier, this thing is 32 years old, and yeah, it's pretty much made in 1990. So that's what we have here. And then here we have a lot of binding posts or sockets for the banana plugs, 4mm banana plugs, and they have the same function as the panels in the front, except a few sockets here. But what we have as the same is these 5 guys here. So high, low, guard, low, high. And of course, here on the left side, the red and blue connectors, those are the inputs. And then these 2 on the other side, the blue and the brown, are kind of outputs, because those are the source panel or connectors for the 4-wire measurement. So that's what we have. And one more interesting thing that is more important for troubleshooting, here it says unit 760 G1. So this is the G unit. And that means that when you look up the manual of this thing, not the operation manual, but more like the service manual, there will be different designations like A, B, C, D, E, F, G, and so on. And they distinguish between the inside of this thing and the capabilities of this thing. So we will see different stuff if we see different letters after the type number, like 7060. So you can see that the back panel of this thing is also quite simple. Nothing sophisticated can be found here. And the only communication, well, 32 years ago was this GPIB, no serial port, nothing else. But yeah, this works well, so it's fine enough or good enough. So that's about the back panel. So yeah, this is the back panel. And after discussing everything, I think I will just dive in. And I will still keep this camera a little bit just to give you an overview. And then I will choose another camera to show certain parts from a close-up shot, because there will be some interesting things. So here is the opened enclosure, and you can see the beautiful circuitry in this device. And you can see that it is full of components, so there is so many components here. And obviously I don't know all the components of this circuitry, so I'm not going to give you a very detailed tour about this thing. I will just mention a few things, but I'm not going to go through this thing, because that would need a lot of research from my side as well. So obviously you could have guessed that here is the mains part, because here is the transformer, and then there is some power supply parts on this panel, as well as we have the digital part, let's say. So part of this panel takes care of the LCD, which prints the numbers. That is somewhere there, and there is a beeper here as well. But then part of this thing also takes care of the digital communication. So you can see this ribbon cable, and this goes to the GPIB port. And then on this side we have the, let's say, more important part. So this is, let's call it as a front end. So of course it has a few relays, for example, and it has also a few precision resistors. I will show you the close-up thing, but yeah, these panels where you switch between the ranges, you switch between the measurement modes, and so on, and where you do the conversion of the voltage, and so on. So you can see that this is a very sophisticated panel, but it looks gorgeous. So I will show you some close-up pictures to really highlight how this thing looks from a close-up. So one thing I want to show you is really close to this important looking chip right here, and that is actually hidden down there behind this white resistor, probably a resistor. So you can see that there is two tantalum capacitors there, and as a reference I show you the color of a normal tantalum capacitor, which is right here. I try to focus on this. You see that blob? It's a nice and yellowish thing, right? But if I try to move back, those are a bit toasty, right? So that's actually one of the issues which I found with this board. And actually one of these capacitors had an escaping PPM there. I will show you a picture because I removed that. But I can show you another thing, which is right here. Here, there is another tantalum capacitor, and there is a PPM which is escaping there. Obviously, it's probably the metal coming outside. So what I try to attempt here is I will actually try to replace these things. So this will be a bit challenging because I will have to remove the wall panel and disconnect a lot of things. But probably it will be interesting challenge as a, let's say, repair challenge. And you can see that the device is working, but I'm not sure how long it will work and how stable it will work if I keep these things like this inside the equipment. And then I will also try to look for some other issues, because probably it's not only that these two capacitors, this guy here and the other at the corner, are dying, but probably something else might also degrade. I mean, this thing is quite old, so I'm not surprised by this thing. Then I can show you this here. It's a nice relay, but you can see those brownish speckles, and those are just corrosion stains, let's say. So it is slowly corroding as well. So that's not so nice. So now what I will do is I will switch back to another camera to show you how I try to remove this panel. And after doing that, I will also show you how I try to, let's say, repair that thing. So let's go to the other camera. So I'm back with the other camera with another perspective, and I somehow need to remove this wall panel because I have the capacitors, well, actually one pair is located here, which looks funny, and another is hiding behind this component there. So I have these copper stubs, and there is 4 of them. So I have to remove that, and then somehow I have to lift out this panel, and then I can go to my desk and try to do the repair on this. So it's free, so we can take a closer look at this, and hopefully I will be able to repair those 4 capacitors. So 2 toasty capacitors are here, and 2 where the PPMs are escaping are here. So I will move to my desk and I will try to replace them. So here is the circuit which I removed from the wall box or enclosure, and I have identified the position of those, or location of those 4 capacitors. So 2 are here and they still have the blobs which are visible, and then 2 others are here. One had a blob, but I removed it before showing it to you, and then other is just toasty, so it is just matter of time to reveal the metal. So let's prevent that. And of course I have already opened the enclosure of this circuit. I haven't removed the PCB itself, but I seen the parts. So I ordered already these actually 10 microfarad and 25 volt capacitors. So I have 4 of them, and I will replace these with the new ones, and hopefully everything will work well. And one test that we can do after I reassembled everything is that I measured the voltages again against my reference, and we will see if we get the same values as I got in the beginning of the video. So let me prepare a little bit and then I will do the soldering. So these are the capacitors which I purchased. So these are 10 microfarad plus minus 10% tolerance and 25 volt capacitors. I'm holding the positive leg right now, you can see it. So these are polarized. So I will have to take care about the, let's say, polarity of the pins inside the board. So I'm just going to desolder them one by one and replace them carefully. I have already took some notes just to remember how they were inside the board. So just before I put back the last 2 capacitors, I want to show you the comparison between the toasted ones and the normal ones. So the top row here, you can see these 4 guys. Those were the removed 25 volt and 10 microfarad capacitors. These 2 on the right side, they are more or less, a little bit toasted, but this one is extremely damaged. So you can see the comparison that they should look like this, a very bright color as compared to these. And as you can see, it has a magnetic legs as well as my tweezer is magnetic. So maybe the next investment should be a paramagnetic tweezer, probably from a proper stainless steel, austenitic one, or something like that. But yeah, now you can see the comparison that the good guys here, these 2 guys, are much more brighter. So now after I replace them, hopefully they will survive a few more years and make this device work well. So I have assembled the board, but initially I had some issues and I want to show you what were those issues. So you can see these, I don't even know how to call them, connectors. And actually what they do is that they connect this PCB at the top with the PCB at the bottom that you can see in the darker area. And at the end of the tweezer, you can see that there are some pins. So actually what happens is that on the bottom PCB, there is a similar type of terminal at the certain points of the PCB, like here in a line. and they look like this, and they accept a very long, probably copper or brass pin, and that pin is visible there. As you can see, the socket is also visible. So then there is the pin, and the pin comes up, and then this or these sockets accept those pins. So first I put everything together, I assembled it, and I turned on the multimeter, and there was always an error on the display. So it showed some kind of overflow, which was indicated by a blinking display and a very funny value. So then I was scratching my head what was happening, and then I discovered that actually these pins can like fall down a little bit, almost by half a centimeter. And in that case, there were a few terminals which were not connected to the bottom of the PCB or to the bottom PCB. So that caused some issues. So I was not able to get the readings. But now it seems that the connections are fine, so I get a reading. So I will put the lid on top of the enclosure, and then we will measure the 3 voltages again, and we will see if I get back the same 2.5, 5 and 10 volts that we got in the beginning of this service. So I put the lid back on and I turn on the machine. So this has been turned on just right now. So it has been running for just a few minutes, and it has been reassembled just a few minutes ago. So of course there can be some changes in the readings because of the temperature and so on. Of course we need this machine to be turned on for quite a while to get, let's say, stable, reproducible readings. But whatever, we are not really concerned about that. I'm just concerned how big the difference is between this reading now and, let's say, before the repair. So now I'm reading the 2.5 volt, and this is what we get, and I put it on the display right here, what was the previous reading. And let's do the same exercise with the 5 volt value. So I plugged it into the 5 volt output, and that is our current reading, and the previous reading is down here on the display, as you can see. And then we do it with 10 volts again. So I let it stabilize for a while, but no, you can already see that it's 9.99611, and here is the previous value on the display. And of course I don't know these values, so I will edit the video and you will see everything, so I cannot comment on the values right now. But what I can comment about is these 4 guys here, 3, 4. So these are the toasty capacitors. Of course I showed you better close-ups than I'm showing you right now because this camera is not capable of doing it, but you can see that these really needed some replacement, not only because they have this very heavy discoloration, but all of them had this metal blob on their outside, which means that metal inside this resin enclosure or capsuling basically escaped. So that's not a good sign. And if you remember, these are 10 microfarad tantalum capacitors rated for 25 volts, and their tolerance supposed to be 20%. So just for fun, I have this tester, and we can test these capacitors. And of course, capacitor testing with these things are quite dangerous. Once I popped one of these, I have an older one, the similar type, but that literally died because I thought I discharged the capacitor which I connected to it, but it was not discharged. So now what I'm doing is basically I'm just shorting out the legs of this thing, so that pretty much should discharge this thing. And this is the toastiest one, the darkest one, so I want to test this. And let's see what we can do here. By the way, this is a modded version. You can see that the bottom is a bit different, because I had problems plugging in the USB charger because the socket there is sitting too deep. So I designed a new bottom cover, 3D printed one, and I also added a switch here because otherwise the battery was dead in a few minutes. Even the full charged battery somehow discharged, even though this unit has a auto off feature that pretty much doesn't work. And it seems like that I left this turned on, so I just got a charger and we turn this thing on. So I got the charging cable. Let's connect this thing. And it says 493.7 microfarad. That's not really the value that we are looking for. So that's not so good. So this also shows that this capacitor is pretty much dead. I can test another one. Let's see, this is the less damaged one. So just for fun, I can connect it quickly and see how it performs. Of course, discharge it first. So this one is less toasted and 12.95 microfarad is the value. And the ESR is 6.3 ohms. So that's what it gives us. Then I just test the rest. This seems to have issues with the testing. Let's connect it again. So it seems like that the device has difficulties testing this one. So it seems that this is really a dead component. And despite the fact that this was dead, it was running. So yeah, that's really funny. I put this here. And then let's test the last one. So let's see what this gives to us. So this is 13.5 microfarad, 2.7 ESR. It's a bit lower ESR, a bit higher capacitor value, or capacity, sorry. And seems like that these two were still okay. The less toasty ones, they come from the same part of the circuit. And then these two very toasty guys, they were killed somehow. So that's not too nice. But at least now I know what was the issue. And this also just proves that it was about time to replace those components. And of course I looked around and I could not find any other components which were, let's say, damaged or have some kind of leakage and so on. So that's really nice. So in this video I just wanted to go through this very old but very nice benchtop multimeter. I really like this device, it's really nice. And yeah, maybe I will make another video where I will try to capture the output of the GPIB port, and then of course using some kind of microcontroller like an Arduino or something, I will try to make a smarter voltage logger or something. So for example, using this very precise device, I will be able to log the voltages or whatever values I'm measuring with this thing on an SD card, or just send it to the computer via USB, and so on and so on. So I will need some time to learn that protocol and learn this device, how to control it, and so on. So that video will come in the future, but probably it will come because I'm really interested in learning the GPIB protocol. So I hope you like this video. I hope you enjoyed this old multimeter. I really like this device. I hope you learned something. If you find this kind of video useful or entertaining, please consider becoming my Patreon. Check the link in the description. Also, don't forget to visit my website because I put some extra pictures and extra resources there. So if you are, for example, interested in the manual, service manual and operational manual there of this thing, I will put it on my website. And yeah, that's all. So I hope you like this video. I hope you learned something, and see you in the next video.